Good morning, everyone. In our last class, we learned about temperature distribution on the Earth's surface according to their latitudinal extension and altitude, that is elevation. In today's class, we are going to discuss about temperature inversion. Okay. After getting more depth in our concept, we have to learn about the normal lapse rate. Okay, what is normal lapse rate? Under normal conditions, the atmosphere gets colder as you go higher. Okay, this is 20 degrees Celsius, and as we go upwards to the surface and from the surface towards the space, it will get less warmer, that is 10 degrees Celsius. Okay, temperature decreases with altitude. Okay, in the troposphere, temperature typically decreases with an increase in altitude. This is known as normal lapse rate. Okay, this is the normal phenomena. The standard rate of cooling is approximately 1 degree Celsius for every 165 meters of ascent. Okay, cooling is approximately 1 degree Celsius for every 165 meters. Okay, this is the normal lapse rate. Okay, now the opposite of this phenomena is known as temperature inversion. Okay, exception, what it is? A reversal of the normal behavior of temperature in the troposphere. It is a meteorological phenomenon where a layer of warm air lies over a layer of cold air. Okay, this is the normal situation. In the Earth's surface, the warm temperature become cooler when it moves from upward in a upward direction. On the other hand, in the temperature inversion situation, with a altitude rising altitude, the temperature will also rise. The temperature will also increase. Okay, in simple terms, the situation is flipped. Temperature increases with the height for a certain altitude. Key characteristics of temperature inversion occurs in static atmospheric conditions or due to the air movement, and usually of short duration but quite common. Okay, this is a common atmospheric phenomenon, and it has a short duration time period, short durability. Now there are some perfect conditions required to happen a temperature inversion phenomenon in the Earth's atmosphere. Okay, 5 key atmospheric conditions favor the formation of a temperature inversion, especially near the ground. Okay, long winter nights, loss of heat by terrestrial radiation from the ground exceeds incoming solar radiation. Then cloudless and clear skies allows for rapid and unobstructed loss of heat from the ground. Okay, calm or slow moving air prevent mixing of heat in the lower atmosphere, allowing cold air to settle. Dry air near the surface limits the absorption of heat radiated from the earth. Then snow-covered ground reflects incoming solar radiation, maximizing the net loss of heat from the surface. Okay, these all long winter nights, cloudless and clear skies, calm or snow-moving air, dry air near the surface, snow-covered ground. These all 5 conditions creates the temperature inversion conditions. Okay. Now there are 4 types of inversion. Okay, temperature inversions are not a single event. They form under different conditions at a various altitude. They are broadly classified based on their formation mechanisms: radiation inversion, subsidence inversion, valley inversion, and frontal inversion. First of all, radiation inversion, that is happening in surface level. Okay, the main mechanism of radiation inversion is it develops when air is cooled by contact with a colder ground surface, okay, until it becomes cooler than the overlying atmosphere. Key triggers are most often occurs on clear and calm nights. The ground rapidly loses heat through radiation. The result is if surface air temperature drops below its dew point, fog may result. Okay, during this type of weather phenomenon, that is radiation inversion, fog may result. Occurrence very common in higher latitudes, occurs during cold nights in lower and middle latitudes, and is destroyed during the daytime. It's not happen in daytime. Secondly, subsidence inversion in upper atmospheric layer. Okay, mechanisms is forms when a widespread layer of air descends. The descending air is compressed and heated by the resulting increase in atmospheric pressures. Okay, this is the descending air masses, that is higher pressure, and warm subsided air, this is inversion layer, and colder surface layer. Okay, result is the air at higher altitudes becomes warmer than the air at lower altitudes, creating the inversion. Okay, occurrence common over northern continents in winter in dry atmospheres and common over subtropical oceans and typically located under large high pressure centers. Okay, the third type of temperature inversion is valley inversion. This is intermountain. Okay, the mechanism is at night the mountain slopes radiate heat and cool down rapidly. The air in contact with the slopes cools and becomes dense and grows heavily. And this cold, dense air drains downslope into the bottom of the valley. This pool of cold air settles at the bottom, while the air at higher elevations on the valley sides remains relatively warmer. Okay, katabatic winds, inversion layer, warm air, cold air drainage. This is cold air pool, and this is the diagram of valley inversion. Okay, that is happening in mountain regions and mountain slopes. The final types of temperature inversion is frontal inversion. Okay, it creates cyclones. Mechanism is occurs when warm and cold air fronts meet. Okay, warm and cold air fronts meet, and the warmer, lighter air mass is forced to rise up and over the colder, dense air mass. Okay, this is a cold air mass, and this is the warm air mass. Warm air mass rises upwards. Okay, rise upwards. And key characteristics are, unlike other types, this inversion has a considerable slopes. Okay, this has a slope. That is, this is a slope rather than being horizontal. It is inherently unstable. Okay, it is not unstable and is destroyed as the weather changes. Okay, results often takes place in temperate zones and causes cyclonic conditions leading to precipitation in different forms. It may create rainfalls. Okay, and different kind of cyclonic conditions. Now. This is a comparative table between these four types of temperature inversion. Okay, in terms of primary cause, radiation, ground cooling through terrestrial radiation, subsidence, descending compressing air in high pressure systems, valley, cool air drainage into low-lying topography, frontal, collision of air and cold air masses. And in types of typical altitude, radiation, surface and ground level, subsidence, upper atmosphere, valley floor and lower slopes, frontal, sloped from surface upwards. Key features, radiation forms on clear nights can create fog, and subsidence, widespread and persistent, associated with high pressure, valley, topography dependent, creates pools of cool air. Frontal, dynamic and unstable, produces weather and precipitation. Okay, now there are some impacts of temperature inversion. Okay, first of all, air pollution, reduced visibility, that is smoke. Okay, an inversion layer acts like a cape, stopping the vertical movement of air and creating high stable atmospheric conditions. Okay, air pollution, pollutants like dust particles and smoke released near the surface are trapped because this is because temperature inversion is stopping the vertical movement of air. Okay, they stop the vertical movement of air. That's why the dust particles and smoke released near the surface are trapped. Okay, that cannot move upward. They cannot disperse, leading to high concentration and poor air quality. Okay, then reduced visibility. This trapped layer of pollutants combined with condensed water vapor forms thick fog or smoke, severely reducing visibility. Okay, these are two impact of temperature inversion. Another inversion is disrupting weather and climate. Okay, less rainfall. The stable inversion layer prevent warm moist air from rising. Convection clouds cannot grow vertically, shifting the process that leads to showers and significant rainfall. This can be a problem for agricultural productivity. Then frost formation. The layer of cold air trapped at the surface can lead to temperatures dropping below freezing, causing frost to form, which can damage crops. Again, minimal temperature swings. Okay, the trapped air and lack of particle mixing mean that diurnal daily variations in temperature tend to be very small. Then it creates storms. Okay, cyclone. While inversion creates stability, they can also act as a pressure cooker. Okay, an inversion can trap a layer of warm, moist air near the surface, okay, preventing it from rising and releasing energy. If the inversion is eventually broken, example by strong surface heating or an approaching weather front, this trapped energy can be released all at once. Okay, this explosive release of energy can fuel the development of intense thunderstorms and even tornadoes. Okay, energy trapped, stage 1, and energy release, inversion breaks. Okay, this is cold air, inversion layer. Okay, these are some impacts of temperature inversion on the Earth's surface. Now, in the conclusion, the concept is normal in temperature will decrease with rising altitude. In inversion situation, temperature and altitude both are increased. Warm air over cold air. And the conditions are long winter nights, clear and cloudless skies, calm and slow air, dry surface and air snow covers. These are all prerequisites for creating temperature inversion conditions. Then types of temperature inversion are radiation, ground cooling, subsidence, descending compressing air, valley cold air drainage, frontal warm front over cold front. Then the effects traps pollution like fog and smoke, creates fog and smoke, and stops vertical air movement, reduce rainfall and visibility, and can fuel severe storms when it's broken. Okay, that's all for today. If you have any doubt and query, just let me know in the comment section. Thanks for watching. Thank you.